Stars dot the night sky, giving an impressive clue to the vastness of the galaxy we live in. I remember being in South Africa on a clear night, far away from any city and its accompanying light pollution. I simply can't describe how spectacular the heavens were. No photo I could show here could possibly give justice to be in that situation, in person, and looking into the seemingly infinite. Some of the dots we see in the sky are stars, all in varying stages of their evolution, and are many light years away from us. But apart from being giant balls of light and energy, how much do we actually know about stars? Where do they come from? Are there different types? And what happens to them eventually? I'm McColgan, and you're watching Astrum, and in this small series of videos, I will go through the lifetime of various types of stars, starting in this episode with how stars are formed. When we think of interstellar space, we often think of a cold vacuum of nothing. And by our earthly standards, it might as well be nothing. But this is not strictly true. Between the stars of our galaxy is what is known as the interstellar medium, or in other words, the matter and radiation that exist between stars. It is comprised mainly of hydrogen, followed by a small amount of helium and trace amounts of heavier elements. It can't be thought of something like an atmosphere. Even in the densest parts, there are only 1 million molecules per cubic centimeter. That may seem like a lot, but in the same space, at sea level on Earth, there are 10 quintillion air molecules, and even in a laboratory vacuum, there are still 10 billion molecules per cubic centimeter. In the more sparse reaches of space, the interstellar medium's density can be less than 1 molecule in a cubic centimeter. But what does this mean in figures that we can wrap our heads around? Well, here's an interesting comparison for you. If you're sitting on a chair, look directly down at the ground. If you were to have a cylinder, the diameter of your eye, drawn from your eye to the ground, there are more molecules in that cylinder than if you were to be sitting at the edge of the solar system and have a cylinder drawn from your eye to the center of the galaxy over 27,000 light years away. Although very sparse, the interstellar medium is thought to make up roughly 15% of the visible mass of the Milky Way. Much of the molecules in the interstellar medium are ionized, and there is a special scientific instrument called WAM that can see the densities of ionized gas in space from our perspective on Earth, and this is what it looks like. This gives you a perspective that there is a lot more matter in the galaxy than you might initially think. The interstellar medium, particularly dust, has a very real effect on us too. Over vast distances, the dust in the interstellar medium acts like a fog, either blocking the view of stars thousands of light years away in the visible spectrum of light, or giving stars a reddish appearance. If there wasn't an interstellar medium between the stars, you would be able to see the entire disk of the Milky Way in the night sky. As I mentioned earlier, the density of the interstellar medium varies greatly around the Milky Way. If you've been watching my other videos, you may have heard me speak about nebula and H2 regions. Nebula are denser regions of the interstellar medium. Some of these regions appear as holes in the night sky. In actuality, they are massive interstellar clouds of gas and dust. And when I say massive, I'm talking many light years across, some many million times the mass of our Sun. You may have seen this famous Hubble image before, called the Pillars of Creation. What you're looking at is an example of these gas and dust clouds. What you can see of the left pillar in this image is 4 light years long. Just to give you some perspective, 1 pixel might just about cover the distance of Neptune's orbit if our solar system was placed right next to the pillar. Incredibly, however, this image is in fact just a small segment of this H2 region called the Eagle Nebula. The nebula is just one of many stellar nurseries where stars are formed in our galaxy. In the background, you can see lighter colors of greens, blues, and reds. These bright colors represent different ionized molecules and are known as the H2 region of a nebula. In this image, greens are hydrogen, red are for sulfur, and blue for oxygen. The electrons freed by the ionization process are continually absorbed and re-emitted, producing the different colours for the different atoms. This is a very similar process to what happens in a neon light. The particles are excited to a higher energy state and eventually release that energy in a wave of light. These molecules are extremely hot, heated by nearby stars to temperatures over 8,000 degrees Celsius. They are also reasonably dense for the interstellar medium, from 100 up to 10,000 molecules per cubic centimeter. The pillars themselves are known as molecular clouds, the densest regions of interstellar medium, from around 100 to about 1 million molecules per cubic centimeter. These clouds are cold and dark at around minus 260 degrees Celsius, and they don't allow light to travel through very easily. In fact, they would be invisible if it wasn't for the fact that some are silhouetted against brighter H2 regions. Because of the density of the molecular cloud, the inner molecules don't interact so much with the UV light of local stars, meaning the molecules stay cool and dark. Incredibly, it is these clouds of molecules and dust that eventually turn into the same type of stars that dot our galaxy and universe. But how? What exactly is the process? Generally speaking, these clouds are stable and would exist for billions of years doing nothing. Look at this example of how gas behaves in a molecular cloud at minus 260 degrees Celsius. Even at this temperature, with very little gravity, the molecules spread out in the cloud, the shape of the cloud supported by a balance of its own gravity and internal pressure. So in order for these clouds to become stars, there has to be a trigger, and there are a few different types of triggers that are thought to kickstart the star-making process. Going back to the pillars, you can see one of these triggers in action in this very photo. Along the outside of the pillars, you can see a sort of aurora of light around them. This is because UV light from hot and bright local stars are blasting the outermost molecules, exciting them to higher energies, has a weathering effect on these otherwise stable clouds. As the excited molecules either escape away from the cloud, joining the H2 region, or they push against the colder molecules further in, compressing them. This pressure can also be created by a supernova shockwave. A supernova is caused by the death of a massive star, a topic we'll come to later on. It's interesting to me though that the death of a star can trigger the birth of others. You may also remember me talking about density waves in previous videos, and it's thought that molecular clouds passing through the Milky Way's density waves can also be the trigger for these clouds to collapse. On a very grand scale, galaxies colliding can cause what is known as starburst within the galaxies. Starburst is when a galaxy produces stars at an extremely fast rate, and it can be seen in these areas of extremely hot blue stars. All these triggers destroy the equilibrium of the cloud, and the internal pressure starts to give in to the gravity of the cloud. This bumping and shoving of molecules within the dense cloud cause the molecules to clump together under their own gravity, gradually growing bigger and bigger as the gravity increases and more molecules are pulled in. Depending on the size of the cloud, there can be hundreds to millions of these clumps that get formed within the cloud. As the density of molecules increases from the initial trigger, interaction between the molecules also increases. The temperature starts to increase. The higher density causes stronger gravity. More molecules from the cloud get pulled in by the increasing gravity. Temperatures rise and gravity continues to increase. The domino effect continues. These clumps in the molecular cloud are the beginning of stars called protostars. The protostars keep getting bigger as long as the molecular cloud surrounding them keeps feeding them material. And to become a true star, a protostar needs to be at least 0.08 solar masses. Should the molecular cloud disperse too quickly, the protostar will become a failed star, or what is known as a brown dwarf. The difference between a failed star and a main sequence star is if the temperature and pressure in the core of the star are hot enough for nuclear reactions to begin. Protostars create energy too, but their energy comes from the impact of material entering the star. A star will hit the main sequence, or the next stage of its life, if the core begins to fuse hydrogen to helium. A brown dwarf doesn't have the mass to do this. As a result, it isn't as hot as a star and will keep cooling off. They are not very bright in the visible light spectrum and would actually appear magenta, red or orange. They can have planets, but the chance of life on those planets is slim, as the habitability zone would be quite small and would move closer and closer to the star as it cooled. But what happens if there is enough mass to form a main sequence star? As material gets sucked into the protostar, the star begins to rotate and material begins to spiral inwards. There are a few objects NASA have photographed that are thought to be protostars where this can be seen. These two arms going into the protostar, impacting at tremendous temperatures. This in turn causes the protostar to rotate faster. The material surrounding the protostar flattens and turns into what is known as a planetary disk. Clumps start to form in the disk too, building up under the same gravity that caused the star. Smaller clumps may build up to become the star's planets. Bigger clumps may begin to form their own planetary disk and may become another star. In fact, this is the most common thing to happen in star formation, our Sun being quite unusual in that respect. Most stars will be in a binary star system. Some stars will have many stars in the same system, all orbiting each other. Had Jupiter been fed more mass during its birth, it too might have become a star. It would have needed a lot more mass though, about 70 times more than it currently has. We should consider for a moment size scales. A typical interstellar cloud is 100 trillion kilometers across, or roughly 10,000 times larger than the size of the solar system. A cloud fragment which forms one or a few protostars is 1 trillion kilometers, or roughly 100 times larger than the size of the solar system. By the time the core of the fragment has become a protostar, its size will be approximately 10 billion kilometers and its temperature of order 10,000 degrees Celsius. Interestingly, as material is fed into these protostars, they can unleash shock waves into the rest of the molecular cloud they are still surrounded in. This in turn can trigger further gravitational collapse and more protostars can be formed. Eventually, the molecular cloud's material will be exhausted, and depending on the size of the cloud, what is left is a star, several stars, a few hundred stars, thousands of stars, or a whole supercluster of millions of stars. Some of these clusters will eventually disperse, and the stars will simply join the rotation of the galaxy, much like our Sun. Although I've talked about all of this matter-of-factly, this is still only a theory of how stars are formed, as actually seeing the formation of a star is very difficult due to the timescales involved, and the fact that these protostars are surrounded by dust that obscures the view. This is one of the huge advantages of the James Webb Space Telescope, due to be launched in 2019. Its ability to see in the infrared gives it a big advantage over Hubble, in that it will be able to see through the thickest of dust clouds and hopefully see protostars in action. Hi, I'm Alex McColgan and you're watching Astrum. And today I'm starting something a bit different. Hubble has released a zip file on their website containing the top 100 pictures Hubble has ever taken. What I will do over the course of 10 episodes is go through these pictures one by one and explain what it is you're looking at. And believe me, some of these pictures require an explanation. Number 1. This spectacular collection of stars is the NGC 1850 double star cluster found in the Large Magellanic Cloud, a satellite galaxy to our own Milky Way. NGC 1850 consists of a main globular cluster in the center and a younger, smaller cluster seen below and to the right. The main cluster is about 50 million years old. The smaller cluster is only 4 million years old. It is composed of extremely hot blue OB stars and fainter red T Tauri stars. T Tauri stars are younger stars that are still forming, so young in fact that they may not have even started converting hydrogen to helium, which is how our Sun produces its energy. Instead, they radiate energy released by their own gravitational contraction. You see, when a star cools, the cooling causes the pressure to drop, and the star shrinks as a result. This compression in turn heats up the core of the star. OB stars, on the other hand, are some of the brightest and most massive stars out there. In this image you can also see the remnants of stars that have gone supernova, leaving behind this super bubble of diffuse gas known as N103, which looks similar to the well-known supernova remnant Cygnus Loop in our own Milky Way. It is believed that the birth of new stars can be triggered by the enormous forces in the shock fronts where the supernova blast waves hit and compress the gas, hence why you find these very young stars in these clusters. Number 2. The Red Spider Nebula, also known as NGC 6537. It's a planetary nebula found near the heart of the Milky Way. What produces nebula is often when a red star is dying, the outer layers of the star shoot off into space by strong stellar winds. Once the atmosphere has dissipated, the hot and bright core of the star emits UV radiation, which ionizes the ejected outer layers. The absorbed UV radiation energizes the gas of the planetary nebula, which produces all sorts of different colors. This two-lobed, symmetric planetary nebula definitely looks like a spider and houses one of the hottest white dwarfs ever observed, probably as part of a binary star system. The star itself is not visible in the image because it's so hot, most of the light it radiates is in the ultraviolet. Internal winds emanating from the central stars have been measured in excess of 1,000 kilometers per second. These winds expand the nebula, flow along the nebula's walls, and cause waves of hot gas and dust to collide. Number 3. This planetary nebula, NGC 2080, or the Ghost Head Nebula, is another member of the Large Magellanic Cloud satellite galaxy. It's called the Ghost Head Nebula because of the two distinct white patches it possesses, which look like ghost eyes. The western patch, called A1, has a bubble in the center which was created by the young massive star it contains. The eastern patch, called A2, has several young stars in a newly formed cluster, but they are still obscured by their originating dust cloud. Because the dust clouds are still around the two sets of stars, astronomers believe these stars are not more than 10,000 years old. The nebula is 50 light years across, and if you look to the left of the picture, you will see a lot of green. This is due to ionized oxygen atoms, whereas with the rest of the nebula, you find ionized hydrogen atoms producing this reddish color. Number 4. The Tadpole Galaxy. Now I've already covered that galaxy in my top 10 most beautiful galaxies video, so if you want to find out more about this remarkable galaxy, I'll leave a link in the description, so check it out. Number 5. NGC 4676, or the Mice Galaxies. Nicknamed so because of the long tail of stars and gas emanating from each of the spiral galaxies. They're both very irregularly shaped, as they are in the middle of colliding with each other, although it is thought that they will eventually form one single spiral galaxy. They are a massive 290 million light years away. Interestingly, in the zip file of the top 100 Hubble images, the image of the Mice Galaxies appears to have another galaxy just above it. After some research and with the help of Reddit, it seems this galaxy is there by accident. I couldn't find anything else on it, so it seems someone in the Hubble team was just a little trigger happy with the clone tool, as this galaxy is not in any other picture I found of it. Number 6. This is the Cone Nebula, part of the bigger NGC 2264, or the Christmas Tree Cluster. If we rotate the image, you can see why. It definitely has a Christmas tree shape, plus the star clusters could be seen as baubles or Christmas lights. This star at the trunk of the Christmas tree is a massive O-type star. Looking at the infrared makes the Cone Nebula stand out very clearly. The nebula is about 2,700 light years away from us, and this section of the nebula is about 7 light years long. The structure and color of the nebula comes from ionized hydrogen, the UV radiation coming from the cluster's young stars. Number 7. This is the Hubble Ultra Deep Field, another picture we have already looked at in another video. Since then though, I have found a very cool animation giving us a 3D view of what the ultra deep field would look like. Each one of these dots is a galaxy, each one containing millions upon billions of stars. In fact, astronomers have counted around 6,000 galaxies in this one image alone. And what is even more interesting to me is that we are actually looking at different times right now. The closer galaxies we see come towards us first in the animation are maybe only millions of light years away from us, whereas at the back of this image are galaxies which are billions of light years away. They may not even exist now. It's just that all the light from these galaxies hit the telescope's lens at the same time, but in actual fact, the further back the galaxy, the further back in time we are looking. Number 8, and we're visiting the Large Magellanic Cloud again. This star-forming nebula is part of a region within this galaxy called N11, and is one of the most active star formation regions in the nearby universe. Zooming out a bit, you can see why. There are so many densely packed star clusters full of young stars made up of the dust and gas of this giant nebula. Zoom out again, and we can see where the original picture fits in. It's hard to think that we can resolve the individual stars in another galaxy, but I'm glad we can, because the end result is breathtaking. The colours of the different pictures are because they were taken with different telescopes, which pick up different light wavelengths, for example, infrared or ultraviolet. Number 9. V838 Monocerotis. This is a red variable star 20,000 light years away from us. In February of 2002, it underwent a huge eruption, increasing in brightness massively, before dimming again as is expected with these kind of eruptions. But then, in early March, it increased in brightness again before dimming once more, and again in April it increased in brightness before dimming again to its previous level before the eruption. It is unlike anything that has ever been witnessed before. At its peak, it was one of the brightest and biggest stars in the Milky Way galaxy, at over 1 million times more luminous than our Sun. We don't know what caused the eruption, but theories abound, ranging from nova outbursts to two stars colliding, or even the star swallowing one of its giant planets. The structure you see around the star is its light echo. Because light to us seems very instantaneous, it's quite hard for us to wrap our heads around a light echo, but it is very much like a sound echo, and the best way I can show you is through this. This marble represents Earth, and the ripple represents the pulse of light which shot out from this star. Unobstructed, the ripple would look like this. But because there was a lot of dust around this star, when the light shot out in all directions, it bounced off the dust and created a second ripple which then reached the Earth. Now this is still in the process of happening, which is why the structure looks like it's expanding. Interestingly, when the star first increased in apparent magnitude, it was so bright that it was shining in blue, as you can see from the outside of the light echo. Number 10. M51, the Whirlpool Galaxy. This was also featured in the Galaxies video, so I'll leave a link in the description if you want to know more about that too. Look up into a clear night sky and you'll see thousands of different stars dotting your view. While they all may look like pinpricks of light from our viewpoint, to some of you keen observers, you'll notice that some of them look slightly different from others. Some are bright. Some are barely visible. Some are white. And others are reddish or even blue. How can that be? Why are stars so different from each other? I'm Alex McColgan and you're watching Astrum, and together we will learn all about the various types of stars and find out what makes them all so interesting. Let's start off by having a recap of where stars come from. Although space is a vacuum, it's not a true vacuum in that there are still tens, to millions of particles per cubic centimeter, like hydrogen or oxygen. These particles make up what we call the interstellar medium. The interstellar medium is surprisingly massive, making up 15% of the mass of our galaxy, the Milky Way. This is a lot, considering that the mass of the interstellar medium is compared to the hundreds of billions of stars found in the Milky Way. The interstellar medium exists throughout space, but it's not evenly distributed. The densest parts are called nebula, which can either be colourful regions of ionized gas or cold regions called molecular clouds. Generally, these clouds are supported by their own internal pressure, pushing out against the inward pull of gravity. But every so often, these clouds collapse because of external sources. When the internal pressure of the cloud is overcome, this causes the particles within them to clump together under their own gravity. As the clump begins to build up, its density and thus gravity increases, causing more nearby particles to get drawn in. These particles begin spiraling inwards and around the center of mass until they eventually impact the central object. With the combination of the force of these impacts and the increase in pressure inside the object, it begins to warm up and spin. This is what we call a protostar, or if you want to imagine it this way, a star in the baby stage of its development. Every star has these humble beginnings, but what happens next decides the fate of the protostar. The molecular cloud feeding into the protostar will eventually run out of material, or the protostar will be ejected away early in its protostar phase. If this happens before the protostar reaches 0.08 solar masses, or 0.08 times the mass of our Sun, the protostar will become a brown dwarf, or a failed star. Should the molecular cloud feed enough material into the protostar that its mass amounts to over 0.08 solar masses, the protostar will eventually become a main sequence star, or, in other words, it will reach the adulthood phase of being a star. Why this 0.08 solar mass cutoff? It's because stars with a mass above 0.08 solar masses are big enough for nuclear fusion to take place in the star's core, where the pressure there will convert hydrogen to helium as a power source. At this mass, as long as there is hydrogen to convert, it is self-sustaining, needing no external source to keep it hot. Brown dwarfs don't reach the mass and pressure at the core needed for nuclear fusion to take place, so they will eventually cool off. Their cool and dim nature means that brown dwarfs are pretty hard to see. There are certainly none in our sky visible to the naked eye. Their dim nature means it's hard to put an estimate on how many there are. There could be a lot more in existence than we currently know about. Zooming in on Hubble's picture of the Orion Nebula shows quite a few brown dwarfs visible against the backdrop of the nebula they formed in. The ones we know about are really interesting, but brown dwarfs could have a whole video to themselves, so maybe I'll save it for another time. So, our protostar has reached 0.08 solar masses. What happens next determines the type of main sequence star it will become. When the molecular cloud eventually stops feeding material into the protostar begins to cool and contract. This increases the pressure at the core until the pressure is so great that nuclear fusion occurs, the reactions of which create an internal pressure which counteracts any further contracting. Or, in other words, the forces within the core of the star are in equilibrium. At that point, the protostar hits the main sequence. But what type of star will it become? Let's have a look at the spectral class chart. I want to draw your attention to this band by here. This band indicates that these stars are on the main sequence. As you can see, stars generally belong within this curve. The lowest mass stars are found to the bottom right of the curve, where the molecular cloud ran out of material early on in the star's protostar phase. These stars are small and cool in a category of stars called red dwarfs. As we go up the curve, it indicates that more mass was fed into the protostar as it developed, and the more mass there is, the hotter the star. As the temperature of the star increases, the spectral class shifts, moving from red to orange to yellow to white to blue. Not only does the spectral class change, but the brightness of the star also increases. But if this is the case, why is this band so thick? Surely it should be a much narrower band if the mass is always equal to the temperature and luminosity. Well, that would probably be the case if all stars were the same age. But throughout a star's adult phase, it is still changing slightly. As a star's hydrogen gets diluted by all the helium it has now generated, it is more difficult for the hydrogen to fuse together. The equilibrium within the star shifts slightly to a smaller, denser, hotter core to maintain the fusion of hydrogen. This means over time, the luminosity of the star increases slightly. A good example of this is our Sun, as it used to be only 70% of the brightness it is now. Going back to the chart, a star that may start here may shift to over here over its lifetime. But as is often the case with anything, there are some outliers and exceptions to the rule. On this diagram, you'll notice this band here. This is known as the instability strip and is full of variable stars. A variable star is a star whose brightness and diameter increases and decreases in regular intervals, giving them a pulsating appearance. Some take only hours to pulsate. Some take weeks. A breathtaking example of a variable star seen by the Hubble Space Telescope is RS Puppis. It varies in brightness by a factor of 5 once every 40 or so days. Because this star is surrounded by a beautiful dust structure, we can see the variable nature of this star through a light echo. Light travels extremely fast, but it still takes a long time to get across astronomical distances. This means we can see the precession of light traveling away from the star, with some rings being dark as the star was dimmer and some rings being brighter as the star brightened. Hubble imaged RS Puppis over a 5-week period, and you can actually see this light echo pulsing. They exist along this strip here because at this mass, the internal structure of the star is more prone to instability due to the ionization of helium in the star's convective zone. Again, perhaps a topic for another video as it gets pretty complicated. Another variable to main sequence stars is what material was actually fed into them during the protostar phase. The majority of the interstellar medium is hydrogen, but there are other atoms out there like helium, oxygen, and even metals like iron and gold. If a star has an abundance of metals, which in the case of stellar structure is anything above an atomic number of 2, it will be redder on the spectrum, and metal-poor stars will be bluer. So, as you can see, there are lots of factors for main sequence stars to be different from each other. These are their mass, or how much material was fed into the star during its protostar phase, their age, have they only just become main sequence stars, or have they had time to increase in brightness, and their composition, are they rich or poor in metal? When a massive star comes to the end of its life, it doesn't go out with a whimper, rather it explodes in majestic fashion, in what we call a supernova. This is one of the most energetic events that we know of. At its peak brightness, a powerful supernova can be as luminous as an entire galaxy. This luminosity doesn't last long, as the energy is expended in a short space of time, perhaps lasting only a couple of days at most. On an astronomical timescale, that is just a heartbeat. So, how often does supernovae occur? There's certainly never been one mentioned in the media recently, right? Well, let's wait together for the next supernova to occur somewhere in the universe. Start the clock now, and stop. Only 1 second. As you can see, supernovae are pretty common, but they aren't all that easy to spot. For one, they have to occur somewhere in the observable universe, and be close enough that we can see them and notice them. But in just the astronomically short space of time that humans have been able to observe other galaxies, we have seen tens of supernovae directly. This image of galaxy NGC 4526, captured by Hubble in 1994, shows a supernova on the outskirts during its peak brightness. Astonishingly, it is so bright. In this image, it appears to be a star in our galaxy. But being in another galaxy means even though it was this bright, only strong telescopes were able to observe it. But what about naked eye supernova events? How often do they occur? And what would they look like? Well, it depends on the distance to us. The most recent naked eye supernova event was SN 1987A, a supernova that occurred in the Large Magellanic Cloud in 1987. This is the only supernova that's been observed up close in our local group of galaxies, as the Large Magellanic Cloud is a satellite galaxy to our own Milky Way at only 160,000 light-years away. At this supernova's peak brightness, it reached an apparent magnitude of 3, meaning that although it was visible to the naked eye, it would have only appeared like another star in the night sky. However, this event was of particular interest to scientists, as they had had the Large Magellanic Cloud mapped out, meaning they could pinpoint the exact star that exploded and view the before and after shots. And the after shots are spectacular. This is the remnants of the star. This ring around it is the stellar material ejected by the star 20,000 years before the explosion, and as the shock wave from the supernova expands, you can see it impact the ring, lighting it up through ionization. But with an apparent magnitude of 3, it's not super impressive for those of us wanting to look up and see something fantastic in the night sky. The previous naked eye supernova occurred in 1604, known as Kepler's supernova. Occurring only 20,000 light-years away, it had an apparent magnitude of -2.5. Much brighter than any other star in the night sky, and even visible during the day. This brightness lasted a couple of weeks. We can now observe the remnants of this supernova using modern-day telescopes. But perhaps the brightest supernova in recorded history was in 1006, with an apparent magnitude of -7.5, meaning it was 16 times brighter than Venus, clearly visible during the day. Thanks to the historical records of early astronomers, we can pinpoint this supernova's remnant too. But even supernova 1006, the brightest supernova on record, was still 7,500 light-years away. Are there any stars even closer than that might erupt in a supernova soon? And if so, what would it be like? As it happens, there are 12 stars that are approaching the end of their lives that would erupt in a supernova less than 3,000 light-years away from us. This is the list of them. One of them, one of the most famous stars in our night sky, is Betelgeuse. Found in the Orion constellation, on Orion's shoulder, this star is distinctively reddish in color. This is because it is a red supergiant, which is really near the end of its life. We don't know for sure when any supernova will occur, as we haven't observed any close enough to look out for telltale signs, but it is expected that Betelgeuse could go at any moment really, although it could also still take tens of thousands of years. It is only a few hundred light years away from us, and it is estimated that it would appear brighter than a full moon when it finally erupts in a supernova. But don't fret, Even at this distance, it is expected that no real harm would come to life on Earth. A supernova would have to occur within 50 light years of us for any harm to befall us, and we just don't see any eligible candidates for that right now. Although, it should be noted that a certain type of supernova can also occur with white dwarfs. If a lot of mass gets fed into these tiny dense stars by other nearby stars, this could trigger a supernova. Because of their tiny and dim nature, we don't have a good understanding of how many there are out there. It is thought that there could be a few hundred of them within 50 light years from us that we don't know about. We do seem to be overdue for a supernova somewhere in the galaxy though. Supernovae are believed to occur every 50 years on average in the Milky Way, yet we haven't seen one with modern telescopes yet. And you can be sure that when it finally does happen, that everything about it will be observed for years to come. Number 11. The Spire. The object is actually a tower of cold gas and dust, part of the Eagle Nebula stellar nursery. The spire is a massive 9.5 light years high. The spire is actually being eroded by thousands of hot young stars found in a cluster just off this image. This haze around the structure is hydrogen gas being boiled off by ultraviolet light, whereas the black regions are denser, more resistant gas. This process may well be producing more stars too, as seen here where the bright heated gas pushes against the dark colder gas. This pressure may well cause stars to form. Stars are also formed within the tower, where dense gas collapses under gravity. These bumps may appear small, but they are actually the size of our entire solar system. The stars will continue to grow as long as there is gas around to feed it. The background of the image is more distant illuminated gas. Blue is ultraviolet light interacting with oxygen, and red is hydrogen. 12. NGC 346. We're now traveling 210,000 light years away to a satellite galaxy of ours, the Small Magellanic Cloud. NGC 346 is one of the most dynamic and intricately detailed star-forming regions in known space. In the center of this region is an intense and brilliant cluster of stars, surrounded by a jagged arch of dark, cool gas. As in the last image, the UV light from these stars is blasting against this gas structure. You can see the wind trail left behind these denser globules. This star cluster also houses the brightest star in the Small Magellanic Cloud. Number 13. The Crab Nebula. This nebula is the remnant of a star going supernova. Interestingly, it is documented that ancient Japanese and Chinese astronomers saw this explosion in 1054. What you're looking at here is the remains of that star, being mostly hydrogen gas. Barely visible at the center of this picture is a neutron star, the ultra-dense core of the exploded star. It is only 30 kilometers across and rotates an amazing 30 times per second. As it rotates, it shoots off two streams of high-powered X-ray beams into space. This is why, when observing the star, it looks like it's pulsating. This star is the cause of the bluish glow of the nebula. Number 14. The Orion Nebula. I must say this is one of my favorite pictures Hubble has ever released. The colors are gorgeous. It looks like it should be in an art gallery, plus there's so much going on. The Orion Nebula houses about 3,000 stars, some of which weren't discovered until this picture was taken. In the center of the bright patch are the four biggest stars in the nebula, arranged into a trapezoid, and they're aptly named the trapezium. Around these stars are extremely young stars that likely still have their protoplanetary disks, as you can see here. These disks of condensing gas could well form into planets in the distant future. At the top left here, we have one star illuminating the surrounding dust, a region called M43. We have more dense gas resisting erosion by UV light, and gas reacting to it. You can visibly see the bow shock from some stars as they resist the stellar wind of the biggest stars. On the left is a cavity wall of the nebula, and interestingly, the dim red stars you see here, these tiny pixels really, are brown dwarfs, sometimes referred to as failed stars. Brown dwarfs are stars that cannot sustain nuclear fusion in their cores like our Sun does. As a result, they're comparably cool, less massive, and not as bright. And finally, the Orion Nebula is the closest star-forming region to us, being over 1300 light years away. Number 15, the Pinwheel Galaxy. We're having a little break from nebula now, and looking at something a lot bigger. The Pinwheel, also known as M101, is what is known as a grand design spiral galaxy. The image itself is massive, and we can take a detailed journey from one side to the other. It is a reasonably close neighbor galaxy to our own, being only 21 million light years away, and is also a similar size to the Milky Way. It has very distinct arms, and an unusually high ratio of star-forming regions for a galaxy, seen where the colours are strongest. This means it's a very active galaxy. The reason for this is because of exploded stars, superheated gas, and material falling towards black holes. Number 16, the Cigar Galaxy. Also known as M82, this magnificent starburst galaxy is remarkable for its ejected flame-like red hydrogen gas. Young stars are being born 10 times faster in this galaxy than they are inside our own Milky Way. This is thought to be because of interactions with its close neighbour M81. They are only 300,000 light years apart, and because of their immense gravity they have these tidal effects on each other. M82 houses the brightest known X-ray pulsar called M82X2, which is the big pink dot in the middle of this picture. It's left astronomers scratching their heads as it's pumping out 100 times more X-ray radiation than something of its mass should be able to do. As a comparison, X2's binary system companion, M82X1, which is the pink dot to the bottom right of X2, is a black hole, but surprisingly it emits less X-ray radiation. Number 17, Cassiopeia A. This is the colourful aftermath of a supernova explosion of a star. It is the youngest remnant of a supernova explosion in our galaxy and is only 11,000 light years away. The light hitting Earth from this explosion would have happened about 300 years ago, although there is no record of any sightings. This could be because the outer layers of the star were already ejected and so absorbed the light from the explosion, but it's not really known why. Incredibly, the explosion shell is still incredibly hot, about 30 million degrees centigrade, and is still expanding at 6,000 kilometers per second. This shell is about 10 light years across by now. Number 18, the Lobster Nebula. This is another beautiful nebula found in the Milky Way, around 11,000 light years away from us. It also contains a lot of protostars, found with dark disks and cocoons of gas obscuring the star's view. This star cluster is known as Pismis 24. Pismis 24-1 was thought to be the most massive star on record, at 300 solar masses. It turns out though, this is actually a multi-star system, and is in fact at least 3 stars, each about 100 solar masses. Even with this reduction in size though, they are still some of the most massive stars that we know about. Number 19, NGC 602. This picture is not just beautiful for its shapes, blues and oranges, but also because of all the galaxies in the background. The reason these galaxies are so clear is because NGC 602 is found away from the center of the Small Magellanic Cloud, meaning there's not so many stars to distort the view. This also makes the nebula a lot easier to study. In the center is a cluster of young, bright stars eroding the dust walls away. And finally, number 20, NGC 1672. This is the last image for this episode, and what we have here is a barred spiral galaxy. It has these 2 arms which come away from the rest of the galaxy. the one on the left being a lot more prominent than the other. This galaxy actually has 4 arms. The final 2 is not so defined and they're tucked away inside the galaxy. And interestingly, these arms do not join at the nucleus, but rather at the end of this straight bar of stars. This is actually why it's referred to as a barred spiral galaxy. Around the bar, the galaxy is experiencing starburst, an extreme amount of star formation. NGC 1672 is an impressive 60 million light years away. We are nearly 1,000 members on Patreon, and it's so exciting to see our community grow. If you want ad-free videos, wallpapers, and to join a community of hundreds that love space, sign up below so we can finally reach 1,000. It's more than a number, it's a milestone for everyone who's been part of Astrum's journey. Each new astronaut makes this constellation bigger, the conversation deeper, and the experience richer for everyone. So if you've been watching from the sidelines, now's the perfect time to join the community.